All right, if we could find our seats, please. Thank you. That works well. Okay, to start the second part of the interdisciplinary aspects session, we'll have a talk from Will Misener about the transition between core-powered and photoevaporative mass loss.
Yeah, great. So yeah, I'm Will Misener. I am a postdoctoral fellow at Carnegie Earth and Planets Lab, slightly longer down the road in DC than I would have preferred. Yeah, so I'm gonna tell you about some work I've been doing on discerning mass loss processes in small planets. And it's great to be at this conference because it means everyone else has already done my introduction for me. So I don't need to convince you that we think atmospheric escape from small planets is important for the demographics of small planets and for their final atmospheric states. And I'm just going to jump straight to how there have sort of been two mechanisms that have been proposed to explain a lot of small planet demographics in the literature. One is called core-powered mass loss. And in some ways, it might be better if we had called it bolometrically driven mass loss or core-assisted. Because what's really happening under core-powered mass loss is that the planets are getting irradiated by the bolometric heat from their host star. And that alone can drive a hydrodynamic wind going from these planets, a Parker-type wind. In the literature in the past, it's usually been modeled as isothermal at the equilibrium temperature. And so under kind of a normal atmosphere, this would drive a big wind when the planet is really big. But as the planet shrinks, that wind gets less and less powerful because there's less and less gas getting up to the sonic radius, which is what determines the mass loss rate. But the way that the cores of these planets, their silicate interiors, come into it is that for small exoplanets like sub-Neptunes, the thermal inertia of their cores is so big compared to the thermal inertia of their atmospheres that it can keep the atmosphere from contracting quite as fast. And so it keeps these atmospheres puffy for longer where they're allowed to be stripped by just the bolometric heat of these stars alone. But as we've gone over in great detail throughout this week, these stars aren't only emitting light, in their bolometric optical wavelengths. They're emitting high energy radiation that can be very powerful in stripping atmospheric mass. And that's, of course, the other mechanism that's been proposed to explain atmospheric escape. And that's photoevaporation, right? So this is the XUV high energy radiation from these host stars being absorbed high up in these planets' atmospheres, heating them up to tremendous temperatures well above the equilibrium temperature, and driving a much faster hydrodynamic wind that can also cause the escape of these primary atmospheres. But it's important that these photoevaporative winds are a lot faster than the kind of gentler bolometrically driven winds, because the XUV radiation of these stars dies off over time, right? It declines after saturation phase. And so a lot of the escape happens very early on in this idea. But the real key to these two processes, photoevaporation and core-powered escape, is that they're not really mutually exclusive, right? We think that these planets might have silicate-rich interiors that provide a lot of thermal inertia, and we think that the XUV radiation is hitting these planets. And so what we want to figure out is when these two mechanisms, what they each contribute to shaping the overall distribution of small planets and their atmospheres. And so the way we've been thinking about that in theory is laid out in this paper by James Owen and Hilke Schlichting last year. And the concept goes something like this, that photoevaporation should dominate as long as the UV energy, so these are these planets just like in cross-section, this is the silicate core, and these blue lines are the UV radiation and these orange ones are the bolometric radiation. And so the UV doesn't penetrate quite as far as the optical light into these planets. But if the UV radiation penetrates inside that isothermal sonic radius that you might remember Roof talking about a couple days ago, then it heats up the wind before it goes supersonic, and so it can greatly increase the mass loss rate. And so that's kind of photoevaporation. But if these planets are puffy enough, the UV radiation might not make it into the sonic radius at the bolometric isothermal temperature. And so then, as Ruth said, right, you can't communicate down to supersonic wind. So the wind is already supersonic when the UV gets absorbed. And so then you're just undergoing kind of isothermal, bolometrically driven escape. And then maybe there's some sort of in-between region where the UV gets absorbed just inside the Bondi radius or the sonic radius. And it's not quite entirely clear analytically what happens in that case, right? Because you kind of have two competing mechanisms. And they wrote down, they sort of just derived from first principles that this transition between the two, between photoevaporation and core-powered escape, should happen when at a roughly fixed ratio in this sonic radius to planet radius. That's about 9 or 1/9 if you want to switch it around. So when the planet is about maybe 10% the sonic radius at the isothermal equilibrium temperature, then maybe you switch between the two. And what we wanted to do is test that out with the Aeolus code that Matthias nicely introduced earlier today. So it's a 1D radiative transfer hydrodynamic code that's capable of simulating these sub-Neptune atmospheres. And so that is what I'm going to tell you about. We've been doing some work with that's going to be submitted very soon to model these atmospheres. And we see this exact dynamic starting to happen. And so that's what I'm showing here. These three panels are the temperature, the density, and the velocity as functions of radius for a like an example sub-Neptune planet. And these are the resultant total mass loss rates of all the species. So we have 4 species in this code. We have hydrogen, molecular hydrogen, atomic hydrogen, and we also have protons and electrons, but I'm not showing them on this plot because they're not as important in this regime. And so what you see is that in this lightest color, in the light orange, this planet is the biggest, so we're just starting it at the largest radius. These T's are the transit radii. And these symbols on the lines are the sonic points. And so you can see for this one, the UV is where these big spikes happen in temperature. But you can see that the UV is getting absorbed way beyond the sonic radius of this outflow. And so the mass loss rate is actually just getting set by the bolometric temperature, right? The temperature at the sonic point is roughly the equilibrium temperature. But as you decrease the radius, the UV can penetrate this isothermal sonic radius, and you end up getting you end up heating the outflow up, and it also dissociates into neutral hydrogen, and you get more photoevaporative escape, and then the UV can penetrate deeper and deeper as you make the planet smaller and smaller. And so what we're going to do in this approach is we're going to model a whole bunch of these atmospheres at different radii and for different equilibrium temperatures and masses, and we're going to see how these vary over kind of the sub-Neptune parameter space. And I guess one more thing I just want to note here is that these, the bolometric sonic point, mass loss rate is actually higher than these photoevaporative ones because this planet is a lot bigger. And so if it was photoevaporative, the mass loss rate would be even higher. And we're going to see that again later. And so what we can do, right, is we can take those simulations I just showed and plot their escape rates. And so first, for comparison, these are sort of two semi-analytic calculations for the purple diamonds are the photoevaporative energy limit for a fixed efficiency factor. And these stars are kind of the core-powered bolometric isothermal at the equilibrium temperature rates. And so you can see that these drop off a lot faster as you contract in planet radius. And first, we can model using Aeolus just with no UV input. And you can see that those match really well with the bolometric isothermal escape rates. And then you can add in the UV luminosity. And this is what you end up getting. So you can see that for the largest radius, right, the UV isn't penetrating the bolometric sonic radius. And so they match exactly with these low UV cases, right? The escape rates are exactly the same. And then at really low radii, you can see that the UV penetrates really deeply and you start to approach the energy limit, the photoevaporative energy limit. And then there's this transition region in between where you're switching between the two. So in this case, the UV is just barely penetrating the sonic radius, and it leads to an intermediate mass loss rate. So you can either think of this as like low efficiency photoevaporation or enhanced core powered mass loss. It kind of depends which you like to call it. And really what this is it's a transition in radius, but it's really a transition in time. So as these planets are shrinking, they're going through these different regimes. When they're very big and puffy and young, they're in this kind of bolometrically driven regime, and then they transition to being more and more photoevaporative as time goes on. And it's good to note that that's actually sort of the inverse of what people had said before, right? That core-powered mass loss is supposed to be this longer process that takes a long time to strip these atmospheres, and photoevaporation is this slower process, is this faster process that happens very quickly. But really, the switch might be the opposite way because of this UV penetration argument. And so this is kind of where you can draw the line of the transition between the two. You can also do this as a function of planet mass and equilibrium temperature. And you can see that so these gray lines are sort of this 1/8 is sort of close to that prediction from the analytics that they did in the 2024 paper. You can see that it matches pretty well. We're getting a slightly different slope maybe in mass, but it definitely scales with mass. So you think bigger planets transition at larger radii, and hotter planets transition at smaller radii. And one thing that's interesting is these are different gammas, which I didn't explain, but these are actually different atmospheric opacities in the upper atmospheres, and that can actually make a difference as to when these transition. And I don't have time to talk too much more about that, but if someone wants to know more about it, I'm definitely happy to answer your question, because I'm almost out of time. So just really quickly, this last thing is we can stitch all these atmospheric mass loss rates together and do a time evolution of these planets using both photoevaporation and core-powered mass loss. And so this is just an example planet. It starts at 5% of its total mass in the atmosphere, and it just evolves for 10 to 8 years. These are sort of arbitrary starting conditions, so don't read too much into the exact atmospheric loss profile. But what I want to draw your attention to is how it compares to kind of two other approximations. So in blue is like a core-powered mass loss only profile. And you can see that they track each other right in this early phase of evolution where there is no, where the XUV isn't able to penetrate the sonic radius. And then they diverge, right? The UV can drive much more loss over the next kind of 100 million years than the core-powered only case does, which kind of flattens out. It stops losing energy or atmospheric mass. And then this red curve is if you don't include the core energy cooling into the atmosphere. So kind of a photoevaporation envelope only evolution. And this one also loses a lot less mass over time than kind of the combined model, because the atmosphere can contract a bit faster if you don't allow the core to cool into the atmosphere. And so this just sort of shows that both processes are going to be important for our understanding. You kind of have to include all the physics that we know about to really capture these planets' evolution in time. And with that, I know I'm running out of time, so I'll just throw out my conclusions, right? That the evolution of small planets involves both processes, and we can determine the transition of these two using these hydrodynamic models, and that it allows us to have this kind of, we can really build this all-encompassing model that includes all the physics that we know about for atmospheric escape. Thank you.
All right, questions for our speaker? Michael?
Yeah, Michael Zhang, University of Chicago. I'm curious about the isothermal assumption for the bolometric case. Like, how close to reality do you think that is, and how much of an impact does that have?
This is a great question that I hope I sort of baited, because it was like a slide that I cut for time. This is actually, we worked this out in a paper that we published earlier this year. And so this is kind of under a core-powered mass loss only assumption, but using Aeolus to model that, because it turns out we hadn't actually done too many hydrodynamic simulations of bolometric escape. And what we found is that the actual profiles you get in the upper atmosphere, of course, don't have to be isothermal. Exoplanet scientists have known this for a long time, right? You can either get inversions, or you can get kind of cool stratospheres. And that depends on your value of this gamma parameter, which is this opacity to incident solar radiation to opacity of outgoing thermal radiation, right? And so if you can change the temperatures and the density profiles in the outer atmospheres, what that means is that you can drastically change the escape rates. So in this particular case, right, you're going either up or down by an order of magnitude at a given time, just based on whether the other atmosphere is cooler or hotter than the equilibrium temperature. And right, we kind of just used these as, we just varied these numbers as numbers, but like what's actually causing these changes are different atmospheric constituents, right, that either absorb better in the infrared or better in the optical. And we're finding that that still does make a difference for, even if you include kind of both photoevaporative and core powered escape. So what this is showing is that these are different radii. So in this one, the radius is deeper. And you can see all three of these get, the UV penetrates the sonic radius, and you get photoevaporative escape. And these aren't very different at really late times. So these are just 3 different values of gamma. But for earlier times, you can see that for the low value of gamma, you actually undergo photoevaporative escape. So the sonic point is kind of at higher temperature. But for these ones, right, the density hasn't fallen off quite as much, and you're still in the core powered regime. So it changes where that transition radius happens. So it can have an effect. Yeah, it does have an effect even for this case.
All right, let's take our speaker again. Alrighty, so next we will be welcoming David Wilson, who's going to speak about the extreme ultraviolet.
Thank you. Yeah, hi, I'm David Wilson from the University of Colorado, and over this conference we've been talking about how important it is to know the EEV flux from stars so that we can do any of the science basically. So I'm going to talk about a couple of programs we have to get that data. But first I want to make one thing very clear. Sorry if you've seen that joke before. I put a lot of work into that slide, so I'm trying to reuse it. Oh, that's a better joke. So yeah, how do we know this EV flux? How do we get this science behind a huge amount of what we've done here? And so why do we need to know it? Why do we need to go out and measure it? Why can't we just model it or get it from the sun, for example? And a kind of driving thing is this. So here I'm comparing 2 M dwarfs to the sun. And I'll turn the laser on. Oh, there. Scaling them to the habitable zone. So the planet in the habitable zone of the M dwarf sees this compared to the Earth seeing it from the sun. And we can immediately see that the EUV flux of the M dwarfs is much, much higher than what the Earth is getting from the sun. And when we're considering the observed exoplanets, we're seeing them much closer into the stars, so that goes up again. So we need to go out and observe this. And so for that, we've been doing for now almost a decade, the MUSCLES program. This is measurements of the ultraviolet spectral characteristics of low-mass exoplanetary systems. I can't say that slowly, don't ask me. And originally, the original idea of MUSCLES and megamuscles was to look at M and K dwarfs and get a representative sample. So look at as many as we could, given the limitations of the observatories we use, and try and get as many, covering a range of spectral types and ages, such that even if we hadn't observed your M dwarf or the M dwarf of any planetary system of interest, there should be one close enough in the sample that you could use it as a proxy. And this is half of megamuscles, by the way. But what we found was that even within quite constrained bins, even within very similar stars of very similar spectral type and rotation period, their high energy flux could vary quite dramatically between them, and also vary in time. Such that even if there are good proxies with similar spectral type, similar rotation period, you really need to go out and observe the star itself if you're interested in any given star. So we moved on to the MUSCLES extension for atmospheric transmission spectroscopy, or MEATS. And this 2 programs going for trying to observe all of the exoplanet host stars that JWST observed in cycle 1, so 11 JWST, ERS, and GTO targets, and then more than 20 JWST geo targets. That took a while. You see, only cycle 1 took us this long to get them all done. And we're now at a stage where we've actually got a pretty good range. So here I'm comparing rotation period and effective temperature of all the targets that we have. If they're a color dot, we have a full SED from the X-ray through to the infrared built for them, publicly available or soon publicly available. And then the gray dots are all the JWST targets that don't have SEDs yet. And you see we're doing a pretty good job, I think. We've got a very good coverage with some gaps. We haven't got anything around here. But overall, we're now filling out this range of spectral types and rotation period. And also, we're going back on ourselves, saying, well, ideally, if we find that stars are different, even if they have similar parameters, but now we've got enough in some regions where instead of picking one proxy, you might want to pick several proxies and see how they're different and see how that affects your results. And what do they look like? This is megameets all powered up on top of each other, again scaling to the habitable zone, and comparing with the sun and Earth. And this is again reinforcing this idea that even with similar temperatures, they're all quite different. So if you just pick a color for temperature, you can see that color repeating across the whole range of the extreme ultraviolet. Like sun-like stars here, there's one right down the bottom, there's one right at the top. This is the very young one that Cindy Froning had a paper on. But again, we found again and again, these stars, you really can't tell from the basic stellar properties what their extreme ultraviolet fluxes will look like. How do we actually go and make, and I put in an obligatory coordinate shoreline plot because everyone's got one. I've changed it, so instead of a cumulative XUV radiation, this is the instantaneous XUV variation, the actual thing that we're measuring. And so this is probably telling you more like, rather than what planets have had their atmospheres survive, this is maybe a guide to what planets are undergoing escape at the moment. And these ones labeled are ones we've detected escape. And in general, pretty good job for the shoreline there. They're all, the escaping ones are all mostly pretty high, but also everything's pretty high. In general, the cycle 1 JWST targets have higher XUV irradiation than the Earth, even in cases where where there are similar distances to the Earth or similar relative distances to the Earth. I'm not sure what that says about our sample selection, or about the physics that we're learning here that we can apply from the solar system or not. Yeah. How do we actually do this? So yeah, we can get X-ray and X-ray data from Chandra or XMM. We get Phi-eV and Ni-eV data from Hubble Space Telescope. Note these are all three are very competitive instruments and also aging instruments. So they're hard to get time on, hard to get repeat time on. These stars are all going to vary, so it'd be nice to go back and observe them again, but that's even harder ask than observe them in the first place. And they could die at any moment, because they're aging. So the amount of time that we're able to do this for is quite limited. But we can't observe the EEV. We can, fortunately, as Kevin was discussing the other day, use what we can learn in the X-ray and the Phi-eV and the EEV to infer the EEV behavior of the sun, of the stars, but the different methods disagree. And if anyone's hoping to fill in the order of magnitude spot on their bingo, I have bad news for you. We are not within an order of magnitude. This is 4 different ways of estimating the EEV flux. So this is the spectrum in the background is what you'll get in a megamuscles or megameets SED. It's the differential emission measure model, which uses the fluxes from Phi-eV lines and the X-ray flux to model the spectrum in between. But you can also scale from the X-ray, you can scale from Phi-eV lines, you can scale from Lyman alpha. All of them disagree. There's over order of magnitude in between these two lines. And then you can put a order of magnitude error bar on them. And why is this? Well, we don't have any data to go on. The Extreme Ultraviolet Explorer in the 90s observed a handful of stars. very unrepresentative of like the range of spectral types we're seeing planetary systems about. So really, we have no idea which one of these is correct because we have nothing to actually test it against. How do we fix that? Well, we build a new space telescope, of course. This is MANTIS. This is monitoring activity of nearby stars with ultraviolet imaging and spectroscopy. The T stands for stars. And it doesn't even do imaging anymore. We've changed it to fully spectra, so it doesn't even make sense. Not mine. But this is a CubeSat. So this is a 16U CubeSat. We'll hopefully launch in 2027. And we will simultaneously observe in the near UV, far UV, and the extreme ultraviolets. This is a diagram of how that all works. We have two telescopes. We have a normal incidence telescope for the far UV and near UV, a grazing incidence telescope for the EUV, and they bounce around, and the far UV light ends up on the detector for the EUV telescope. It's quite a fun design, and it all just about fits into a box, and obviously packed in with a load of other electronics. And because the technology has improved so much, because it's been so long since we've had an EUV telescope, here is Extreme Ultraviolet Explorer and MANTIS roughly to scale, but we actually get about twice the effective area of the EUV telescopes on EUVE. Don't get as good spectral resolution, but we're massively improving in sensitivity, so we'll be able to go after all of the faint EUV targets that EUV couldn't. Two missions, two more acronyms that I can't even remember. So while JWST is observing a exoplanet transit, we aim to be observing simultaneously with MANTIS, getting a 5e near UV, if we're 5e in near, yeah, wait, 5e in near UV, and if we're lucky, an extreme ultraviolet light curve as a spectroscopic light curve as the planet is transiting, so we can see what the star is doing while the JWST data is getting gathered. And then while JWST is doing something else, we'll be monitoring hopefully about 20 nearby stars, trying to get a range of spectral types and ages to finally get that data that we need to test the EV models and see if we can actually measure the EV flux coming from stars. Yeah, oh, I'm right on time. I hope. I just wasn't paying attention. So to conclude, yeah, we need these X-ray and UV observations. They're really hard to get, but we've been getting, have over dozens of stars. You can get them at this QR code. I'm glad to report the QR code still works. I was very worried by the poster that had expired QR codes. We found that JWST cycle 1 targets generally have more EV flux from the Earth. Question mark about what that means about our sample, but we don't really know what the EV flux is. It's very hard to get, but we're going to try with MANTIS soon. Thank you.
Questions for a speaker?
Yeah.
Huge body of work. Awesome, David. I am curious, Park Lloyd, Eureka Scientific. You mentioned that similar effective temperatures can have quite a spread in their spectra. I'm curious if that's true as well when you factor in rotation period.
It gets better. It doesn't go away. Okay. So yeah, so you're going to be more similar rotation period, but we still have found quite a spread, even if we plot against like Rossby number or something. You still get quite a spread in the EV flux.
Do you have a number off the cuff? Like
really?
roughly? Okay.
Yeah.
Could you say a bit more about the JWST planets? Generally, we see more EUV flux than Earth.
Yeah. Again, with the huge caveat that like it's tricky to measure the planets, but so here's all of them against Earth to the habitable zone, and so this is Sun at Earth, and you can just see like in general they're higher. And then this gets worse when we actually scale them to the actual planets JWST is observing, because they're generally closer than Earth. Yeah, I don't have a good explanation. We didn't set out to find this. Maybe there's some selection effects going on here. I don't know what it would be, but I'd thought that planets would be easier to find around quieter stars, so we'd expect them to be less active. Yeah, that's a real question for the audience, I guess, of why are we preferentially looking at stars that have high EV fluxes, high X-ray fluxes?
So
yeah.
is it true for all the planets that you looked at, or all the JWST planets that you looked at?
In cycle 1, yeah. Well, this is cycle about half cycle 1. It's I'd say generally true. They're not all, like some that are lower. But yeah, in general, yeah, they seem to be higher than the Earth's EV flux.
Very interesting.
Yeah. Well, I guess one source of bias is we may be deliberately going after planets that are escaping and thus like have high EV fluxes because we think they have escaping atmospheres. But I'm not sure.
One more question.
Go over there, I think.
So since we don't know much at all about the EUV, how are you deciding which 20 targets to point mantis at? Like, is it about ISM in between, or like?
Yeah, and so the real drive, because it's a CubeSat, will be what we can observe in the time. It's very hard to plan these observations with CubeSats, but we're going to be targeting low hydrogen column density so that we have a chance of seeing the EUV flux. Not too limited, because as I said, we've got twice the effective area of EUVE, so we can actually go, if it's got an EV detection, we can definitely go for it. But we'll be trying to get as good data as we can, so low hydrogen column density.
All right, let's thank David again.
Hello guys, today I'm going to talk about the relative roles of several different atmospheric escape mechanisms by incorporating them into a subneptune evolution framework. To begin with, the role of atmospheric escape in shaping planetary evolution and the population has been widely discussed in the past decade. And there are two mass loss mechanisms, core mass loss and the photoevaporation. Their relative roles has been under debate. I don't want to introduce more. Thank you for introducing the background for this. Actually, there is another mass loss mechanism that has been understudied, or at least underrepresented at this workshop. It's called boil-off. Boil-off is triggered by disk dispersal. Like when the disk is starting to dissipate, the confinement pressure declines so that it's harder and harder for the planet to achieve hydrostatics in the atmosphere, so that it has to outflow following a Parker wind. It operates on mega-year timescale, so it's a very short-lived escape. You see that there is no fundamental difference between the outflows in corporate mass loss and boil-off because they are both Parker winds. The only difference lies in the interior, how they interact with the interior. I will talk about this later. Before that, I'm going to show you the schematics of the evolution framework that I developed in the past years. It's called CMIST. So CMIST has some improvements. It improves upon previous subneptune model by incorporating this kind of a rocky core evolution. It calculates the solidification process within the rock and iron core. It calculates the energy transport in there compared to the previous model where people typically assume that the core is isothermal perfect conductor. And another remarkable improvement is that we incorporate real hydrodynamic calculation for photoevaporation using WINDY, as presented in Ruth and Maddie's talk. This can improve the accuracy on the mass loss rate estimate compared to the previous subneptune model, which usually rely on energy-limited escape or tabulated hydrodynamic results. And we also incorporate hydrohelium dissolution, which I will not cover here. Now let's talk about the differences between boil-off and core mass loss. It's only about the role of core luminosity, so there are two effects. The first difference is that the core luminosity keeps the envelope inflated because it heats up the envelope from the bottom. This can lead to enhanced mass loss rate because the particle wind is very sensitive. The particle wind mass loss rate sensitively depends on your radius. So the larger the radius, the faster the mass loss rate because of the scale height is large. It makes the pressure gradient larger to push the material up. So here is an example showing you the radius, envelope radius evolution with and without core luminosity. You see there is a 20% difference. But this is sufficient to drive a large difference in the mass loss rate. However, we found this effect not only impacts core part mass loss, but also impact any long-lived mass loss, as long as thermal contraction and mass loss are coupled together. In that case, it also impacts photoevaporation. So in some work, it's called core enhanced photoevaporation. So here, we follow this terminology. So we only think that it's a mass loss effect rather than a distinct mass loss mechanism because it happens to any long-lived thermally driven escape. But we also find that its effect on boil-off is, however, is limited because the mass loss rate is just too fast. The time scale is too short. Like within one mass loss time scale, the envelope does not have sufficient time to contract, so that whether or not you have core heating does not change the mass loss very much. So let's move on to the second difference. So based on the original argument in Ginsburg et al., people argue that when you are taking mass through the outflow at the surface of the envelope, you have to replenish the material over here. Otherwise, the density over here will be depleted and the wind has to stop. So they argue that it is a core luminosity that lifts the material and replenishes the mass over here. Based on this, they formulate this kind of an energy limited escape. This is a central difference, so I'm gonna tell you that actually we find it's not the case. We agree with them that if the envelope is bottleneck, it can generate an energy limited escape. But we find that the envelope re-equilibration actually does not consume energy because here I'm illustrating this. Like when you are lifting material from the deep hotter part of the envelope to the shallower colder part of the envelope, you are not only overcoming gravitational energy, but also releasing internal energy, which powers this process. And we have done self-consistent calculation, both analytically and numerically. We found that actually it does not consume energy. The only structure layer that consumes energy is the radiated atmosphere. It tells you how much energy you need to lift the material from here to the sounding point. Here you can here is a comparison between the new energy estimate here and the original energy estimate here. You can see there is a huge overestimate from previous study. We actually identified the true bottleneck, which usually happens in the radiative atmosphere, which is primarily stellar heating driven or bolometric driven. We found that when the mass loss rate is high, but your stellar heating is inefficient, it can be bolometrically limited. This leads to energy limited escape. Or in the deep atmosphere, it's strongly dominated by the planet's own cooling. If the intrinsic luminosity there from the planetary cooling is not sufficient, then it can lead to another energy limitation in there. So by incorporating those new understandings into actual modeling, we found that both boil-off and core part mass loss are severely less energy limited, which leads to a faster mass loss rate and a shorter time scale. Here I'm comparing between the previous evolution as in Ginsburg et al. It leads to a long-lived slow mass loss over giga years. Here are the examples. I'm isolating the effects from each of these energy limited escape regime. But in actual modeling, I self-consistently determine which one the planet is in at a given time. You see that they all converge to a certain mass fraction by the end of boil-off. And after boil-off, there is just no long-lived escape because boil-off strongly removes material, making the planet small, and the escape is not efficient after that. So here are more examples. Basically, I'm showing you the fractions after a certain time under boil-off and core pattern mass loss as a function of mass and incident flux. In triangles, those are the mass fraction after boil-off, and we additionally evolved the planet to 3 GeA and the core pattern mass loss. You see there is a small difference between them, indicating that in all of the planets we modeled core pattern mass loss is inefficient long term. So we self-consistently model the transition between photoevaporation to boil-off. We did this numerically, but not in a full hydrodynamic calculation. But we get very similar results as in Will's talk and the Owen and Schlichting paper. It happens very early on. It happens right after boil-off ends. That is a few mega-years old. So at each time step, we calculate like energy transport rate, thermal structure, physical structure, and the physical state and the mass loss. And we evolve the planet following this information. And this is how we do that. We combine together the interior modeling, which is a hydrostatic part in here. This is the temperature pressure profile of the interior. You can see this is iron core, mantle, envelope, and the lower radiative atmosphere. And above 1 microbar, we model the steady state hydrodynamic photoevaporation using windy. This is the temperature profile for it. You see there is a distinct behavior between hot Jupiters and the superpuffs here. So using the new framework, we identified a new photoevaporative mass loss regime. It's called thermal energy mediated photoevaporation. Traditionally, people use this energy limited escape, as seen in many previous talks, in sub-Neptune evolution modeling. However, it's only valid for high gravity planets, especially when radiative cooling is inefficient. But in low gravity planet, we found that it's not the case because there are more energy sink terms than gravitational energy. This is because the gravitational potential well of a low gravity planet is very shallow. It's very easy to lift material. This process does not consume that much energy. What is the bottleneck is actually how much energy you need to maintain the wind temperature that generates suitable pressure gradient for the outflow, as well as accelerating the material to the sound speed. And those terms are in proportion to the temperature, which we collectively call thermal energy. So in low gravity planet, we found that it's a thermal energy dominated, which strongly impacts the escape rate. By working out the mass, we found that the escape rate is in proportion to the input energy over temperature. It's very different from the energy limited escape. Here I'm showing you the numerical result in dotted and analytical results following our formulation for the thermal energy mediated escape, which is temp, in red, and energy limited escape in blue. You see that there is a good match between them. And remarkably, the transition between the two regimes happens over here, which correspond to the time when gravitational energy turns comparable to thermal energy. And this temp regime is very important in sub-Neptune evolution modeling. As you can see, at the young ages, energy limited escape overestimate the mass loss rate by a factor of 10. And this temp regime lasts for a long time in low gravity planets, like hundreds of mega years to exceeding giga years. We found that for any sub-Neptunes that have experienced the boil-off, it will first undergo this temp regime before entering the energy limited phase. So it happens in nearly all of the low mass sub-Neptunes. So using the framework, we can successfully match the observed mass and the radius at the observed age for those superpuff planets. For Kepler-Freedom-B, it's a little bit trickier because the JWST observation shows that it might have a clear atmosphere rather than a hazy atmosphere. But the key point is here, on the bottom, I'm showing you the mass fraction versus age. So the first sharp decline in here corresponds to the boil-off phase. You can see it basically removes a huge amount of mass within 1 mega year. After that, the photoevaporation slowly removes material, but plays a minor role in the mass removal. So this leads to the key takeaway here. We found that boil-off actually accounts for most of the total mass loss, whereas photoevaporation plays a minor role in shaping the total mass, envelope mass. But it's still important because the last few weight percent sensitively determines your radius. So we argue that photoevaporation still shapes the final population a lot. We found long-lived core mass loss negligible. So I'm going to leave my summary here and answer your questions.
Questions for our speaker? I know there's at least one.
Great work, Yao. Park Lloyd, American Scientific. I was curious if you could dive a little deeper into the explanation about, as I understood it, needing the core luminosity, like the Ginzburg formulation was the core luminosity helped replenish the mass that was lost from bolometric radiation. But you found that there was enough energy in the gas itself that you don't need that. Could you just explain it a little more deeply?
Yeah, right. So as you can see in this formulation, people formalize the energy limit escape by looking at how much energy is available from the core heating from the bottom, and how much energy you need to lift the material from this core envelope interface to a larger radius. Is that estimated to be like GMC or RC? But in reality, they only consider the change of binding energy. They ignore the change of internal energy. Internal energy is in proportion to the temperature. Like when you are lifting material from the deep, hotter part of the interior to the shallower, colder part of the interior, it exchanges internal energy. That internal energy is used to lift the material. And we worked out like this, like for an adiabatic non-steady envelope, you can prove that this process always does not consume energy, indicating that the internal energy is the exact release, is the exact amount the gravitational energy you need. Yeah.
Wonderful. Okay, thank you.
One.
Great talk, so, I'm very interested, of course, in the Kepler 51 evolution. I'm just, if you can flip to that. Yeah, so I'm wondering, right, that as you move forward in time, it actually doesn't get that much smaller. It doesn't lose that much more mass.
Right.
Seems to be the case. Is that just because it's cooler, it's farther away from its star? Like, based on your picture, photoevaporation should still matter right after boil off, but
yeah, for this specific case, for superpuffs, we found that it's necessary for them to form at a larger orbital period separation because it decreases the atmospheric escape rate and helps them retain more primordial hydrogen helium mass so that they can be puffy at a late time. So yeah, we don't find much mass loss after that because the bolometric flux, the XUV flux is small for this specific planet. But the relative role, the relative amount of mass removed by boil-off and photoevaporation is roughly fixed if you vary different fluxes. Because when your XUV flux is stronger, then your bolometric flux is also stronger, indicating that during the boil-off phase, you expect a higher equilibrium temperature. That can lead to more mass. So yes, they scale in this way, so that this key conclusion remains like the same, roughly.
Thank you.
Great. Well, let's thank Yao and everyone else in the session.
Before you all go to your merry ways for the rest of the day, we have a group photo in front of the institute right now. So let's all go there.
Sorry, on the patio or outside in the front?
In